Hello everyone, this is Yunpeng Guo from Sichuan University, China. Today, I will briefly introduce our paper entitled Rethinking Safe SSL, Transferring the Open State Problem to a Closed State one. Conventional semi-supervised learning assumes that the unlabeled set derives from the same distribution as the labeled set, which is called a closed set. For example, in the following picture, the labeled set and the unlabeled set share the same categories, that is, cat and dog. In contrast, Safe SSL investigates a more challenging and realistic open set problem, where the unlabeled set contains some out-of-distribution data with unseen classes. For example, butterfly cock in the figure. Most current Safe SSL methods aim to identify the OOD data and then just discard them. However, we got a new inspiration from class activation map. As observed below, for indie data, the model is mainly concerned with the high-level information of the objects. But for OOD data, due to the lack of corresponding categories of objects, the model can only pay more attention to some common category-agnostic low-level information, such as color, age, and corner, which is simultaneously implied in the majority of OOD data. Furthermore, in the TSNE experiment, we found that the OOD data show a clear tendency to gather in the feature space. This inspires us to solve the safe SSL problem from a new viewpoint. That is, we can treat all the OOD data as an individual class paired to other seen classes during training. In this way, we can transfer a k-way classification task on the open set to a simple k+1-way classification task on the closed set. Then we can tackle the complex safe SSL task in the same way as a trivial SSL task. Specifically, our framework mainly contains two stages. The first stage aims to pre-train a prototype network on both labeled and unlabeled data, enabling network to generate accurate prototypes of k-seen classes. Then, we employ a distance-based function to distinguish the OOD data from the indie data, and model the prototype of all OOD data, thus turning the k-way classification to the k+1-way classification. By regarding the prototype of OOD data as new class peer-to-seen classes, we solve the safe SSL problem in a simpler closed-set way in the second stage by utilizing the common SSL techniques, pseudo-labeling and consistency regulation. In addition, to make full use of no-confidence pseudo-labels, we further propose an iterative active learning paradigm to enforce the network learning knowledge from complementary labels on wider classes. Herein, we maintain a memory bank to save the historical negative labels after each iteration. Then, we can iteratively update it to cover more negative classes in the next iteration. With all the more comprehensive complementary labels, our framework can be enhanced to classify more confidently. Our framework is trained with cross-entropy laws on labeled data, consistency laws in consistency regulation, positive laws in pseudo-labeling, and negative laws in iterative lective learning. The experimental results are shown on the right of the poster. Obviously, our proposed method outperforms the sorted approaches on all datasets with different mismatch ratio. Particularly when the mismatch ratio is 0.3, our method achieves 72.5 accuracy in average on Safer 100, about 4.1% higher than Safe Student and 2.7% higher than T2T, which performs best in all other methods. The TSN evaluation shows our method can perform better by reducing the intra-class distance and increasing the inter-class distance. All the classes, including the OOD data marked in black, can be better distinguished. The ablation studies further demonstrate the effectiveness of each key component of our method. In summary, we rethink the safe SSL problem from a novel aspect. By training the OOD prototype as equivalent to other indie prototypes, we transform the safe semi-supervised classification problem from open set to closed set. Therefore, we can solve safe SSL using standard SSL techniques. Extensive experiments on popular benchmarks demonstrate the effectiveness and the superiority of our method. That's all. Thanks for your time and attention.